So what I talked about a bit yesterday, and we'll talk about some more today, is the Merkle-Hellman subset sum crypto system. So we start with an ordered set of integers. So we have positive integers. They don't have to be in increasing order. There's some ordered set of integers. And for every subset, I of the set of numbers from 1, 2, 3 up to n, we form the subset sum, summation m sub I, for all the i's in I. So what this means is, for example, suppose we take I is the subset consisting of the numbers 3, 5, and 6, then the corresponding subset sum, I'll call this S sub I, say. You add the third number plus the fifth number and the sixth number. An equivalent way of doing this is to say, for every binary sequence of length n, so I is a binary sequence, say epsilon 1, epsilon 2, epsilon 3 up to epsilon n, where each epsilon I is 0 or 1, then we have the subset sum, which is summation epsilon mi, I going from 1 up to n. So this means epsilon 1 m1 plus epsilon 2 m2 up to epsilon n m sub n. But of course, these coefficients are 0 or 1. So this is really just the sum over all the m sub I, where epsilon I is equal to 1 and not equal to 0. So there's a one-to-one correspondence between subset sums of the set I and binary sequences. So to every binary sequence I, we associate a subset sum S of I. And the inverse problem would be, given the subset sum S of I, compute I. So this is given a set of numbers and another number, which is a sum of a subset of the numbers, reconstruct the subset. And that can be easy or it can be hard. That reconstruction problem is easy if your set of numbers, the m's, increase very fast. So we say that a sequence m1, m2, m3, up to m sub n, this sequence is super increasing if each m number, m sub I, is at least 2 times the previous number. I going from 2 up to n. So you go start with 3. 6 is 2 times 3. 59 is bigger than 12. 207 is bigger than 2 times 59. This is a super increasing sequence. If you take 3, 6, 9, this is not super increasing because 9 is less than 2 times 6. It's not greater than or equal to it. So this sequence is not. This sequence is super increasing. Okay. And a super increasing sequence has the following property. If M1 up to Mn is super increasing, these are positive integers. This is super increasing, then in fact, for all k from 2 up to n, if you take the sum of all the numbers less than, take the sum of the first k minus 1 numbers, this is always strictly less than the kth number. And the proof of this is by induction on k. First of all, M2 is at least twice M1, so it's bigger than M1. So it's true for k equal 2. What about k equal 3? Well, M3 is at least 2M2 because the sequence is super increasing. And 2M2, they teach you somewhere in preschool, is M2 plus M2. And M2 is strictly bigger than M1. So this is strictly bigger than M2 plus M1, which is what we had to prove for k equal 3. And we could continue like this. If you take k equal 4, M4 is at least 2M3, which is M3 plus M3. And we just saw that M3 is strictly bigger than M2 plus M1. So the statement is true for k. And suppose the statement is true for k minus 1. K minus 1 is at least 2. Then, so this means that M1 up to M sub k minus 2 is strictly less than Mk minus 1. What about Mk? Well, Mk, because the sequence is super increasing, is at least 2 M sub k minus 1, which is Mk minus 1 plus Mk minus 1. Mk minus 1 is Mk minus 1, but Mk minus 1 is also strictly bigger than Mk minus 2, all the numbers down to M sub 1. So it's true for k. So if this inequality is true for k, it's true for k plus 1, so it's true for all k. So one property of a super increasing sequence is that each term is strictly larger than the sum of all the smaller terms. And from this, we can easily compute the summands in a sum. So suppose that M1 up to Mn is super increasing. And suppose we let S be the subset sum of elements of the set of these numbers, of the M sub i's. So S is equal to M sub I1, Mi2, and so forth, up to M sub I sub k, for some integers, distinct integers, I1 bigger than I2, bigger than I3, and so forth, bigger than I sub k. And the question is, how do you find these numbers? Well, what can you say about S? You know that S if it's mi1, mi2 up to mi sub k, all of these numbers, this is a sum, this is less than m sub I1 plus the sum of all the numbers up to I sub 1 minus 1, m1 plus m2 up to m sub I sub 1 minus 1. Because these are all numbers between 1 and I sub 1 minus 1. So it's less than, I should say, less than or equal to the sum of all of these. But by the inequality we just proved, this is strictly less than m sub I sub 1, which is 2m sub I sub 1, which is less than or equal to m sub I sub 1 plus 1. Because in the super increasing sequence, each term is at least twice the previous term. So if you choose the largest element of the sequence less than or equal to S, that's it, say that's mi1, that's less than or equal to S. And let me say this better. Just say it like this. So given S, choose the largest M that's less than or equal to S. Okay. See how I'm saying this. I'm not sure I'm saying this is in the most elegant form. We know that S is a subset sum. If M is so let's say the largest M less than or equal to S, let me just call it M sub K. So M sub K is less than or equal to S and less than M sub K plus 1. Because the next bigger number would be too big. This is the largest M less than or equal to S. So S minus M sub K is greater than or equal to 0 and less than M sub K plus 1 minus M sub K. And there's something here I'm not saying as nicely as I would like. So if M sub K is less than or equal to S, when you write S, okay, This is all true, but let me just try and find a more clearer way of writing this. So we have the sequence called script M. It's consisting of the numbers M1, M2, M3, up to M sub n. And this is super increasing. So each M sub I is greater than or equal to M sub I minus 1, twice M sub I minus 1, which implies if you take the sum of the first I minus 1 numbers, that's strictly less than M sub I. So let S be a subset sum of M. Let M1 be the large, I shouldn't call this, well, I'm calling it M1. So listen, let M1 be the largest element of the sequence M with M1 less than or equal to S. Now I want to look at S minus M1, which is greater than or equal to 0. And this is also a subset sum. Yeah. Yeah. So we have S minus M1. Let's see what happens next. Choose the largest Mi less than or equal to S minus M1, and we'll call it M2. So M2 less than or equal to M1. And we know that M2 can't be any bigger than M1, because this is less than S, and M1 was the largest number less than or equal to S. And I want to show that M2 is less than, strictly less than M1. But if M2 were equal to M1, then two M1 would be less than or equal to S. S is a subset sum. So if S is M, I'm writing this backwards. Increasing or decreasing? I mean, it's clear what's going on, especially clear you look at examples, but so suppose S, let me do it the way I prefer that. AI1 plus AI2 up to MI sub K. So these are the numbers, this is the subset sum. And I1 less than I2. I1 greater than I2, greater than I3, greater than I sub K. Okay. So what can I say about S? S is greater than or equal to M sub I1 because that's one of the summands. And S is also less than the sum of all other numbers up to I1, which is less than M sub I sub 1 plus 1. Because we just proved the lemma that each number in the super increasing set is strictly bigger than the sum of all of the preceding numbers. So if I take S and I choose, and if MI1 is the largest summand, then S is strictly less than M sub I sub 1. So M sub I1 is the largest element of M, which is less than or equal to S. So then I consider S minus M sub I1. So this is MI2 up to MI sub K. And by the previous argument, if I let MI sub 2 be the largest, MI sub 2 is the largest element of M, less than or equal to MI sub 1. And S minus MI sub 1 is strictly less than S. And if I look at S minus MI1 minus MI2, that's less than S minus MI1, which is less than S, and greater than or equal to 0. So as we continue this construction, at every step, we choose the largest element of M less than or equal to S. We know S is a subset sum. We know S is a sum of distinct elements of the sequence M. And we can reconstruct those elements step by step by always choosing the largest element of M we can as a kind of what's sometimes called a greedy algorithm. You do the simplest thing, choose the largest number you can, and eventually you get to your result. So let me just look at an example. In the exercises in the review sheet, number 12, we have a sequence R consisting of the numbers 1, 3, 7, 18, 51, 132, 277, and 612. And you can check just by looking that this sequence is super increasing. Three is greater than or equal to 2, 7 is greater than or equal to 6, 18 is bigger than 14, 51 is bigger than 36, 277 is bigger than 264, and so forth. So this is a super increasing sequence. We want to find a subset sum Well, we have a subset sum S equal to 332. We want to find the numbers in this set that add up to 332. So step 1, find the largest element less than or equal to 332. That's 277. And 332 minus 277 is 55. Step 2, find the largest element less than or equal to 55. That's 51. 55 minus 51 is 4. Step 3, find the largest number less than or equal to 4. That's 3. 4 minus 3 is 1. The largest element less than or equal to 1 is 1. So you put this together and we have 332 is 277 plus 51 plus 3 plus 1. So we've decomposed 332 into a sum of elements, numbers chosen from this set. What about if we take S equal to 673? The largest number less than 673 is 612. 673 minus 612 is 61. The largest element less than 61 is 51. 61 minus 51 is 10. The largest element less than 10 is 7. 10 minus 7 is 3, which is an element in this set. And we have that 673 is 612 plus 51 plus 7 plus 3. So what that tells us is that it's easy to find the subsets, the summands in the subset sum if you have a super increasing sequence. But if it's easy for you, it's easy for everyone else. So you can't base a code on the fact that simply having a super increasing sequence, which allows you to encrypt a number, because it's super increasing, it also allows everyone to decrypt. That is, we have the following bad crypto system. We have a sequence M of n numbers that's super increasing. We start with our message we want to communicate, our plain text message M, which is a binary sequence. This is an n-bit binary sequence. And from M, we compute the subset sum, summation epsilon I m sub I goes from 1 up to n. Epsilon I is 0 or 1, because this is a binary sequence. So whenever it's 0, you get 0. Whenever it's 1, you're picking out one of these numbers and adding it. So you get this subset sum. So this is how you might say you encrypt. But then, so this is, but then to decrypt, we have an algorithm. Which is choose the largest m sub I at each step. And you'll recover the m sub i's that occur in the sum So you know in your binary sequence where you have a 1, and you will know where you have a 0. But of course, the reason why this is bad is anyone can decipher the message. There's no cleverness involved in that, and no difficulty. But the Merkel-Hellman clever idea is not to use the sequence M, but to change it in a way that's simple, but makes the decryption effectively impossible unless you know the key. So in the good crypto system, of Merkel-Hellman, you choose your choose and publish. Well, sorry, you don't publish. Choose super increasing sequence R. R1, R2 to R sub n. So each term is bigger than twice, at least as big as twice the preceding term. Then we choose positive integers A and B, with B bigger than 2Rn. And so the sum of all of these numbers is less than 2Rn. So every subset sum is a positive integer less than B. And we want to choose A and B such the greatest common divisor of A and B is 1. And then from R, we construct a new sequence, M, by multiplying each element of R by A. Right, this is AR. So this is the sequence. M1 is AR1 mod B. M2 is AR2 mod B, and so forth. In general, the ith term of this sequence M sub I is AR sub I reduced mod B. So this is a sequence of n distinct integers, because the r's are distinct mod B, and A is relatively prime to B. So A times R is going to be a number relatively prime to B, and they'll be distinct. We have n integers, but it's not super increasing anymore. Okay. Now, how does this crypto system work? Oh, I should say, so we have Alice and Bob. Alice starts with the sequence R. She chooses numbers A and B, and she constructs the sequence M. And what she publishes is M. So the whole world knows the sequence M of n distinct positive integers not in increasing order, just some order, but everyone knows this. Now, Bob wants to send Alice a secret message. The message is some binary plain text M. So some sequence of zeros and ones. And the encryption is the subset sum S I'll write this as sort of a dot product. What this means is summation xi mi, I goes from 1 up to n. Sorry. Yeah, no, that's right. Binary plain text X. So Bob has his secret message X in binary. He wants to send it to Alice. From X, he computes the subset sum, and he transmits S. And Eve, who is lurking in the shadows, she grabs S or copies S. So Eve knows S. So what does Eve know? Eve knows that S is an integer, which is some sum of a subset of M, because M is public. This is the public key that people can use to send Alice a secret message. And why is it secret? Eve knows that there's some unique subset sum of the M's that is a subsequence of the M's that adds up to S, but she doesn't know how to find it. This is just the practical fact. No one knows how to invert this problem for a large set of integers that don't have some structure. Eve can't do it. And Alice couldn't do it unless she remembered her key. Her key are the numbers A and B. So Eve can't do anything with S, but Alice receives S, which is some sum of these numbers, capital M sub I. And because Alice knows A and B, she also knows A inverse. So Alice computes A inverse S. What is A inverse S? It's A inverse summation xi mi these i's one from n to n. This is summation I goes from 1 up to n, x sub I, this number A inverse, m sub I, mod B, but m sub I is AR sub I mod B. So A inverse M sub I is R sub I mod B. So Alice gets the number S and she multiplies it by A inverse and reduces it, looks at the congruence class mod B. That's a number S prime. And her S prime is a sum of numbers from Ri. The super increasing sequence. By the algorithm, she can recover what these numbers are, so she knows the x's. And so she has decrypted Bob's message. She gets the message she's supposed to get. That is this Merkel-Hellman knapsack crypto system, as it's called. Let's look at the review problem, the review sheet where there's a problem on this crypto system. Let's say number 14. In number 14, R is the world's simplest super increasing sequence, just the first 8 powers of 2. 1, 2, or 9 powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. If you check, this is 2 to the I, where I goes from 0 up to 8. choose A equal to 11 and B equal to 600. So we want to compute the sequence of M's. Yeah, there's a typo. This is really M goes from 1 up to 9. Let's see. So M1 is, so every M sub I is congruent to A R sub I mod B, where M sub I is congruent to 11 R sub I mod 600. So M1 is congruent to 11 times 1 mod 600. So Mi1 is 11. M2 is 22. M3 is 44. M4 is 88. M5 is 11 times 16, I think is 176. M6 is 11 times 32, which is 352. M7 is 11 times 64, which I believe is 704, which is congruent to 104 mod 600. M8 is 11 times 128, which I think 11 times 128, which I think is 1408. If you divide that by 600, you get a remainder of 208. And M9 is 11 times 256 mod 600. 11 times 256 is, if I do my arithmetic correctly, 2,816. Let's see, 2,400 subtracted from that, it's 416 mod 600. So this is my R sequence, and my M sequence is the numbers 11, 22, 44, 88, 176, 352, 104, 208, and 416. Suppose we choose the plain text X to be the binary sequence 1101010001. So this is the sequence M, the order matters. So we're going to get the subset sum S, which is the first term, plus the second term, plus the fourth term, plus the sixth term, plus the ninth term. So what is that? 460, so 388 and 322, it's 410. 410, this is 826. 826 and 33 is 859. So that is the ciphertext that Bob sent to Alice. And how does Alice decipher that? So she computes S prime congruent to A inverse S mod B. So A inverse S is the number such that 11 times A inverse is congruent to 1 mod 600. So we must solve the congruence. Just write X for A inverse. No, that's not good choice. We must solve the congruence. 11A inverse congruent to 1 mod 600. So the only method that we've learned from the text is to compute the greatest common divisor of 11,600, which is 1, and then write 1 as a linear combination of 11 and 600. So let me do the Euclidean algorithm here. 600, if you divide it by 11, goes what? 11 into 600, 5, 50, 100, 9. Oh, that's pretty quick. So 50, 4, 6.
Excuse me, Professor, I'm sorry. I know you're doing number 14, but how did you translate like part B again, like the binary to the plain text, like on the previous page?
Oh, okay. So that's a good question. So let me just review what we had. We started with a super increasing sequence. The powers of 2 from 1 up to 256. We choose A, or Alice chooses A equal to 11, B equal to 600, and the greatest common divisor of 11 and 600 is 1. So we get a sequence M. So this is, let's say, R1 up to R9. And in general, we choose M, we solve the congruence M sub I times A, 11M sub I, 11R sub I, M sub I is congruent to 11R sub I mod 600. So when I multiply each of these numbers in order, I cannot change the order. I multiply each number in order by 11 and look at the least positive congruence class, mod 600. So I get the numbers 11, 22, 44, 88, 176, 352, 104, 208, 416. And then I have, so this is what is public. This is the public key. So the plain text that Bob wants to send Alice is the binary sequence 1101 01 001. So this is X. And then you compute S to be X times M. This means 1 times 11 plus 1 times 22, 0 times 44, 1 times 88. Wherever there's a 1 here, so this is a sequence. These are like the corresponding numbers in the sequence. Wherever there's a 1 here, you add up the number. 111, 122, 88, 352, 416. So S is going to be 11 plus 22 plus 88 plus 352 plus 416. So if I add that up, see 88 and 352 is 440. This makes it 856, 878, 889. Is that what I got when I did it the last time? No, 859. Let me just check. 11, 22, 88, 852. Oh, when I did the arithmetic here, instead of writing 352, I misread my writing. This is 352. And when I add this up, this was 389, I think. Let me just check again here. So this is 768 plus 110, 878, 889. So this is what is sent. This is what Bob sends to Alice. And to decipher this, Alice computes the number S prime, which is A inverse the inverse of 11. It's A inverse times S mod B. That means S prime is whatever is the inverse of 11, I have to calculate that, times 889 mod 600. So I have to find the inverse of 11 mod 600. So if I take 600 and I divide it by 11, I get a quotient of, let's see, 11 into 600, 55, 50, 44, 6. I get 11 times 54 plus 6. 11 is 6 times 1 plus 5. 6 is 5 times 1 plus 1. So if this arithmetic is correct, that means 1 is 6 minus 5. 6 minus 5 is 11 minus 6. So this is 2 times 6 minus 11. 6 is 600 minus 54 times 11 minus 11. This is 2 times 600 minus 2 times 54, 108, minus 1, minus 109 times 11. And this is, in fact, this is correct because this is 1200 minus 1199. So this says that 109 times 11 is congruent to 1 mod 600. So if A is 11, A inverse is 109. So S prime, which is A inverse S mod B, that means S prime is 109 times, what was S? 889 modulo 600. So you have to do this arithmetic. You can do it on a computer, you can do it on a calculator. You can also do it by hand, I think. Let's see. Plus 109 is 109. Mod 600, 889 is 289. Mod 600. Let's see, what is 289 times 109? 9 nines are 81. 9 eights are 72, plus 8 is 80. 9 twos are 18. plus 8 is 26, 0, 2, 8, 9. So it looks like if I can multiply, this is 1, 0, 6 and 9 is 15, 1, 3. So 31,501. If I divide that by 600, this is coming up to a knockoff to 30,000. 1501, knock off 1200, congruent to 201 mod 600. Now, let's see if this is correct. So I have S prime is 200, and I want to write 201 as a subset sum of the super increasing sequence R. And I can see right away that I made a mistake somewhere. Let me just see. I mean, the method I'm using is completely correct. Just somewhere doing this by hand, I have to correct my arithmetical errors. So I have my super increasing sequence R, the powers of 2 from 1 to 256. I multiply by 11 and reduce mod 600. So I get 11, 22, 44, 88, 176, 352. 352. Hopefully I did this correct. So 11 times 352, 2783. See this number, maybe I just did my calculation wrong. Sorry, this is 64 times 11 is 704, which is 104. No, that's right. This corresponds to 64. And 11 times 128 should be 208. And 416. So this is my number M. Then my binary sequence that I'm encoding is 1101010001. So that gives me the number 416 plus 352, which is 8, which is 768. 52 and 16 is 68, 768, plus 88, plus 22, which is 110, plus 11, which is 121. I get 8. Sorry, I get 988. So this is correct. So the number that, the encrypted number that Bob sends to Alice is 889. Then that's S. Okay. And then to decrypt this, you take what this number is congruent to when you multiply it by the inverse of 11 mod 600. And I computed the inverse of 11 mod 600 is 109. So I have to take 889 times 109. And for some reason, I wrote 289 here. So it's just my sloppiness. Let me do the arithmetic correctly. So 889 times 109. 9 nines are 81. 9 8 are 72, plus 8 is 80. 9 eighths are 72, plus 8 is 800. So this is 8,001. 0,988. So when I add this up, I get 10978. 10979. So S prime is congruent to 109 times 889. Which means S prime is congruent to 97,901 mod 600. So if I divide 600, and again, just do it the hard way. 600 divided into 97,901. This goes once. 973, 0. This goes 6. 600. So this is 190. Bring down the 1. This goes 3. 1800. This is 101. Congruent to 101, not 600. And again, that cannot possibly be correct. I mean, the reason I know it's not correct, so I have S prime is 101. So then I'm going to write S prime as a sum, a subset sum from my original super increasing sequence. And we'll say 101 is 64 plus 32. It's 96 plus 4 plus 1. So let me write it like this. This is 1, 4, 32, 64. You can compare this to the R sequence, 1, 2, 4, 8, 16, 32, 64, 128, 256. This would correspond to the binary sequence 1, 0, 1, 0, 0, 1, 1. What was the sequence I started with? One, 1, 0, 1, 0, 1, 0, 0, 1. So something is wrong. And I'm just going to have to do it again because I like to get these things right. And so let's let me go. R are the powers of 2 from 1 to 256. We choose A equal to 11, B equals 600. Greatest common divisor is 1. Okay. The sequence M we get by multiplying every number in R by 11 and reducing it mod 600. So we get 11, 22, 44, 88. We're just doubling it every step. 176, 352. But then when you double 352, you get 704. Reduce that mod 600, that's 104. Double that, double that. So this is the sequence M. Okay. Then I have my bit sequence, my binary sequence, 1, 1, 0, 1, 0, 1, 0, 0, 1. So the numbers I'm going to add up are 11, 22, 88, 352, and 416. When I do that arithmetic, I get 121, plus 8,
Excuse
68.
Professor. I don't
Yeah.
mean to interrupt you, but are always like are they always gonna like correspond and be like the same length? Like the you see how the plain text is like x equals this? Like is there ever like a point like where x is like smaller, like where x is just 1 1 0 1
No,
and
no,
then
no.
that's
If
it?
it's smaller, then you have to add zeros at the end. But you
Hmm.
want to take the product, you want your bit sequence to be exactly the same length as your super increasing sequence and as your sequence of m's.
Okay.
Okay. So, I mean, when you're doing cryptography, however long your message is, you break it in, it's a bit sequence, it's a binary sequence. You
Hmm.
break it up into blocks of some predetermined length. Like every block is going to have 500 letters, 500 digits. So
Hmm.
you break your system, your text might have 2 million digits, but you break it up into successive blocks that are like 500 digits long. And if it doesn't go evenly into the number, your last block will have fewer digits, so you just add some zeros. So these have to have the same length.
Okay.
So let me see again if I can add correctly. This is 768, 790, 801, 889. So the number that I am encrypting and sending is 889. And then if I calculated things correctly, 11 inverse mod 600 is the number 109. That is 109 times 11 is congruent to 1 mod 600. 109, 109, 9911. Oh, I think that's my mistake. 109 times 11 doesn't leave a remainder of 1. How did I get that? Oh. One is 1200 minus 1199. So, well, one is 2 times 600 minus 109 times 11. So, the inverse, right, so I think this is my mistake. So this says that minus 109, right, times 11 is 1. So the inverse of 600 is minus 109, which I have to write as a positive number, is 491. So A inverse, this is then all wrong. A inverse is 400. $491 mod 600. It's minus 109. So S prime is going to be 491 times my S. What was S? 889. $889 mod 600. So S prime is congruent to 491 times 889 mod 600. And again, I can take a piece of paper and multiply these out by hand. I can take a calculator and do it correctly in a second. Or I can open my computer to Maple or whatever is your favorite computer program and calculate what is 491 times 889 congruent to mod 600, and I get 299. So my S prime is 299. And then I have to decipher that. So remember, what is my sequence of R's? It's 1, 2, 4, 8, 16, 32, 64, 128, 256. How do I write 299 as a sum of numbers in this sequence? You do it by the greedy algorithm. The largest power of 2 you can pick is 256. 299 minus 256 is 43. The largest power of 2, no bigger than 43, is 32. 43 minus 32 is 11. The largest power of 2, no bigger than 11, is 8. 11 minus 8 is 3. 3 is 2 plus 1. So this says that my binary sequence X, I put a 1 wherever I have the same number and 0 where the number is missing. 1, 1, 0, 1, 0, 1, 0, 0, 1. And now I did it correctly. I recovered X as the binary sequence 1, 1, 0, 1, 0, 1, 0, 0, 1. That's what it was. So that is the Merkle-Hellman algorithm, the knapsack crypto system. Yeah. All right, that took a little bit of work. Sometimes you have to do some work. All right, any questions about this or anything else that's maybe on the review sheet that you would like me to do?
Yes, Professor.
Okay.
What's
Yeah,
it?
go
You
ahead.
go first.
No, go ahead. No, thank you. Go ahead.
Let's see here. Could we go over let me see what questions we have here. Could we go over like number 17 possibly?
Number 17. Okay. So the Elgamal crypto system is, we start with a plain text and we create a ciphertext that has 2 numbers in it. So, and let's go and see what is the way to do this. So this is the Elgamal crypto system.
And Professor, just to confirm, what's it? Elgamal, RSA, and
Well,
the
there are 4
Diffie-Hellman.
encryption schemes we have.
Like all 4 of them will be
Sorry.
on the exam,
Actually, no,
right?
sorry, there are 5. So the first thing we did was the RSA public key crypto system.
Yeah.
And we also did, you can sort of do it in a certain sense backwards. and you get the RSA
Signature.
digital signature system.
Mhm.
Then we had the El Gamal crypto system, which I'm about to do, the knapsack system, which I did a few minutes ago, and the Diffie-Hellman key exchange.
Mhm.
And the mathematics involved are factoring,
Mhm.
discrete logarithms, and subset sums. Okay, so problem 17, we start with a prime p equal to 17. Sorry, yeah, problem 17. And a primitive root g equal to 3. And Alice sends the, so what does Alice do? So Alice has a private key A, and she computes the number capital A, which is g to the A mod p. And she publishes A. And we're told that A is equal to 5 in this problem. So we don't know, we're not told what little a is. We don't need to know it at this point. But A is equal to 5. And the prime p is known. Well, in fact, what's known are the prime, the primitive root, and the special key 5. Okay. Now, Bob has the message, the plain text, m equal to 13. So he chooses a random element, a random number k equal to 3. Sorry, in problem 17, k equal to 2. And he wants to compute C1 and C2. So C1 is going to be g to the k mod p. G is 3, k is 2, and p is 17. So this is just 9 mod 17. So C1 is equal to 9. C2 is going to be his message times a to the k mod 17. The message is 13. A is the number he got from Alice, 5 to the 2 mod 17. So this is 13 times 25 mod 17. Let's see, 12 times 25 is 300. So this is, I think, 325 mod 17. And if you divide this by 17, I think you get a remainder of 2. Seventeen into 325 goes 117,551. 17 into that goes 9. 9 sevens are 63. Yeah, 2. So C2 is equal to 2. So this message that Bob sends back to Alice, C1, C2, is the pair 9, 2.
Thank you, Professor. So what's it the equations for C1 and C2 will always be the same, right? Like how g of k mod p and then C2 is m of a to the k in
Yeah.
terms of like the problems. Yeah.
Yeah, that is the El Gamal crypto system.
All right, thank you, because I wanted to like ask, because like I didn't know like if like like you could like change the thing, but it makes sense that it stays the same for for C1 and for C2.
Was there another question, Fatima?
No, thank you, Professor. I was wondering actually, is it possible if I have any question tomorrow, can I ask you a question tomorrow about the review?
Yes.
Okay, thank you.
Yeah.
Thank you for your time.
Yeah. At the 11 o'clock session, you can ask me any question you like,
Thank you so much.
other
Thank you.
than what is on the exam. But yes.
Of course, I got it. Thank you. Thanks.
Okay. Anything else?
Can you just go over how the decryption works for the AlgoML, and then
Yeah,
that's it?
okay.
Because I was I was doing like some of the homework on that, or like looking at some of the reviews, so I just wanted like clarification for like how
Sure.
you encrypt and decrypt for it.
Okay. So let me do number 18, which is the decryption part of it. So in number 18, again, we have prime P equals 17, primitive root equal to 3, and the public key A is equal to 5. So that's the information that's known to the world. And Bob sends to Alice the pair 8, 2. So C1 is 8, C2 is 2. And we're told that Alice's secret key is A equal to 5. So what Alice computes is the plain text X is going to be C1 to the power A inverse times C2 mod P. So C1 is 8. This is 8 to the 5th minus 1 times 2 mod 17. Mod 17. Okay. So I have to know what is the inverse. So must find, I don't know, let's call it T, such that A to the 5th T is congruent to 1 mod 17. Okay? That's the inverse mod 17 of C1 to the A. That is A to the 5th. So let's see how we can do this. So what is 8 to the 5th? Let me compute 8 to the 5th. 8 squared is 16 is minus 1 mod 17. So 8 to the 4th is 8 squared squared is minus 1 squared is 1 mod 17. So 8 to the 5th is 8 times 1 is 8 mod 17. 8 times minus 2 is minus 16, which is 1 mod 17. So the inverse, an inverse of 17 of our number is minus 2, which is the same as 15 mod 17. So this number is 15, and 2 times 15 is 30, which is 13 mod 17. So M, what we're looking for, the answer is 13.
Thank you, Professor. So basically you solved the equation on top, the 8 to the 5th, what's it,
Inverse.
inverse 2 mod 17, right? Was that
Yes.
17? Okay. And
So
then
I have to compute the inverse of 8 to the 5th mod 17.
Mhm.
And I did it an easy way. I mean, I could have computed the 8th power, the
to
5th power of
the
8,
fifth, and then
which
find
is
the
some big
inverse.
number, and reduce it mod 17, but
Mhm.
my way was quicker.
Yeah, because but that's one of the ways I I did it was like for like the homeworks I did like 2 to like the 5th or something, and then I
Oh,
took the inverse and then like in the mod and stuff like that and breaking it down.
actually, it looks like what I did was completely wrong, though. It was 8, I did 8 times 2 instead of 8 squared.
Yeah, 8 squared would be
It's
64.
64.
Mm-hmm.
And 64 mod 17 is what? 3468 is, this is minus 4. So when I take 8 to the 4th, that's 8 squared squared, that's minus 4 squared, that's 16, which is minus 1. And so 8 to the 5th is 8 times minus 1, which is minus 8, which is plus 9. Yeah. So I made an arithmetical mistake again. So this should be 9. So I'm looking at 8 times 9. Which is 72. And I reduce that mod 17. Let me just check. So 8 squared is 64. 64 plus 4 is 68, which is divisible with 17. So 8 squared is minus 4. So 8 squared is congruent to minus 4 mod 17. So 8 to the 4th is 16, which is minus 1. So 8 to the 5th is minus 8, which is congruent to 9 mod 17. So I need to find the inverse of 9 mod 17. So I need to solve 9 times something. 9 times 2 is congruent to 1 mod 17. So the inverse is 2. And so this is 2. So it should be 2 times 2 is 4. The answer should be 4, I think, if I did this right. But you just have to check the arithmetic. I mean, that's the arithmetic right there.
Professor, I'm sorry to bother you. Is it possible to go for over number 5, please, if you don't mind?
Number 5.
I'm sorry, last
Yeah,
minute.
sure. No problem.
Thank you.
So review problem 5. So suppose I take G equal 2 mod 17. So what are the powers of 2? 2, 4, 8, 16. 16, let's see. 2 to the 4th is 16 is minus 1 mod 17. So 2 to the 8th is 2 to the 4th squared, which is minus 1 squared, which is 1 mod 17. So the smallest power of 2 congruent to 1 mod 17 is 8. And for a primitive root, it has to be 16. So this proves that 2 is not a primitive root. If you take the powers of 3 mod 17, you get 3, 9, 27, which is 10 mod 17. Just keep multiplying by 3. So let me do it more neatly. 3 to the first power is 3. Everything is mod 17. So 3 squared is 9. 3 cubed is 27, which is congruent to 10. 3 to the 4th is 3 times 3 cubed, which is 3 times 10, which is 30, which mod 17 is minus 4. 3 to the 5th is 3 times 3 to the 4th. That's 3 times minus 4, which is minus 12, which is congruent to 5, mod 17. 3 to the 6th is 3 times 3 to the 5th, which is 3 times 5, which is 15, mod 17. Or minus 2, if you like, makes it easier. 3 to the 7th is 3 times 3 to the 6th, which is 3 times minus 2, which is minus 6. 3 to the 8th is 3 times 3 to the 7th. That's 3 times minus 6. That's minus 18. That's minus 1, mod 17. Now, whatever is the power of 3, so if 3 to the k is congruent to 1, mod 17, then k must divide 16. So the only possible powers of k are 1, 2, 4, 8, 16, or 16. Well, we see 1 doesn't work, 2 doesn't work, 4 doesn't work, 8 doesn't work, so the answer has to be 16. So 3 is a primitive root. Okay. I don't know. Did I do that too quickly? I'm not sure.
No, it's good. Thank you.
Right. And then you need to find the discrete logarithm of 11 mod 17. So the third part is to compute. So we know 3 is a primitive root, mod 17. So if we want the logarithm of 11 with respect to the base 3, if we want to find what is this number, let's call it x. So x has the property that 3 to the x is congruent to 11 mod 17. So you have to take the powers of 3 until you get 11. You see here, when we took the powers of 3, we started to get, we got 3, 9, 10, minus 4, which is the same as 13, 5 minus 2, which is the same as 15, minus 6 is the same as 11 mod 17. So 3 to the 7th is congruent to 11. So the discrete logarithm of 11 with respect to the base 3 is equal to 7. That's problem number 5.
Thank you, Professor.
Okay,
Thank you, Professor.
sure. Okay, see you tomorrow. I'm also
Have a good
around
day.
tonight at 7 on Zoom.
Okay, thanks.
Bye.